stopping and starting the flow of a gas when it's at atmospheric pressure like this, it's easy. But what if that gas is coming at 1,000 bar? What materials do you need? What kind of things can even do this? That's what we're going to look at today. And for this, I'm joined by an expert in that field, Markus Wirth. He's a mechatronics engineer and has been engineering valves for the last 8 years or so. You work for Bürkert, that is a company that has expertise in fluid control system. Thanks for Markus for coming. And hopefully answering all my questions.
Yes, thank you for inviting me.
Perfect.
My pleasure.
So I see you didn't come alone. You brought something along. What are these?
Yeah, these are our ultra high pressure valves up to 1,000 bar, and for comparison, also low pressure valves.
Okay, so ultra high pressure valves, that's what we're talking about. Maybe tell us, what is exactly an ultra high pressure valve as compared to a normal valve?
Yeah. So in general, high pressure is a wide range for most customers that are working in the pressure area.
Yeah.
And for everyone, it's a little different what is really low pressure and high pressure, depending on what they are used to.
So.
And for ultra high pressure, we are we are talking about valves over 350 bar, because then you have some mechanical changes compared to the lower, only just high pressure valves.
Okay, so yeah, I see you brought a bit of a chart for that here. So basically you say everything above 350 is what you would say is ultra high pressure, because you have different mechanical properties also that are, does the physics change? Is it different from my normal bicycle tire valve?
It's a little different.
Yeah. Okay.
So in general, with low pressure, we are using a deep drawn tube, for example.
Yeah, okay. Yeah?
This is made from sheet material and then punched, bringing into this form.
Okay.
And it's maybe 0.5, 0.6 millimeters.
Yeah.
And then the plunger
that comes inside there. Okay.
is in here.
Okay.
The magnetic plunger, magnetic stopper. And then when you open the valve, this is how it works in general.
So this is a low pressure valve side moves. Okay.
This is a low pressure valve. Yeah. We feel comfortable with these kind of tubes to go up to 100 bar.
100 bar, okay.
Yeah.
So
here.
Okay, that's that. So then we now go to the higher pressure valves.
Right.
So what's the difference? Maybe show us a little bit of a difference there.
So high pressure, you can see it here. Now the tube is not deep drawn anymore. It's now machined from full bar material.
When you say the tube, it's this part
here,
This is the tube.
And now it's maybe up to 2 millimeters thick.
Yeah.
Because you need this for the new working pressure, the burst pressure, and so on.
Okay. So it is thicker, and it's machined differently.
Yeah.
Okay. So So now we know. For you, ultra high pressure is everything higher than 350 bar. So we're talking like up to 1,000 bar, maybe even a little bit more.
Maybe a little bit more, right? Yeah. Because the US wants 50,000 PSI, so technically that's 1,035.
All right, you can trust them for overtaking the other. Okay, so Markus, take us inside. How does an ultra high pressure valve work?
Okay, so. When I just come back to the low pressure variant,
here
the
tube, show that in here.
The tube here is welded with the magnetic stopper, as it is here.
Magnetic stopper.
Yes, this part here.
This is what you call the magnetic stopper. Okay.
It's fixed.
Yeah.
And then it stops the plunger.
Okay. So
after opening the valve.
So this kind of moves. Yeah.
Yeah.
Okay. And just to understand the valve, so you brought an open valve, so normally you would see it like this, right?
Yeah.
And then when you look inside, where's the gas coming from? From this side or from this side?
So you can do both.
Both, okay.
But especially at high pressure, usually you come from here.
Okay.
And then the pressure touches all around the plunger.
All right.
And presses it on the seat, so you have an additional tightness through the pressure.
So the pressurized air or gas is coming from this side.
Yeah.
And basically, so if I want to open it, then I have to work against that and pull this up, basically.
Right, yeah.
Okay.
So the spring brings the plunger down.
Yeah.
And is tightening the seat.
Pushing down, yeah.
But much more challenging is high pressure.
All right.
It's much more force than the spring.
Yeah, okay, so exactly. So this is low pressure. Show us high pressure.
Yes. I just wanted to tell you that here with this high pressure up to 350 power, we are still welding here.
Yeah.
But now with the ultra high pressure valves, this is now completely screwed.
Okay.
So the magnetic stopper up here is screwed to the tube because we don't want any welding anymore at this high pressure area.
Okay. So just to be clear, this is an ultra high pressure valve.
Yeah.
Also same way, I could see an arrow even. So basically gas in on this side, gas out on this side. And in the same way, where was it? In from this side. So it comes in here.
Yes.
And that's interesting. It goes through this narrow tube here.
Yeah,
So it
that's
actually in the valve is the narrowest spot of the transfer, is it?
Yeah. The narrow spot is here, right?
Yeah.
Down
there.
below the plunger.
Okay.
This is what we call the valve seat. And in this valve, it's only 0.7 millimeter, the diameter.
0.7 meter diameter. Coming from, wow, what do we have here? This is almost, okay, I don't know what will be like, maybe like 5-6 millimeter.
Yeah.
Yeah, so 0.7 millimeter you have here.
Yeah.
Okay, cool.
And this seat defines the flow rate for the valve. Yeah.
Okay.
And in general, how a solenoid valve works.
Yeah.
It's you have a coil, of course,
yeah,
like
okay,
this,
like that
a
one.
lot of windings,
Yes.
and then you actuate it, and a magnetic field develops.
So this is a coil like this.
Yeah.
And you put in a current.
Here you
obviously.
put in the plug, the current, right?
Yeah, okay.
And the one side is connected through all the windings to the other side.
Yeah, okay. Well, you have a third one here.
Yeah, that is for grounding.
All right, okay. So that creates a magnetic field.
Right, yeah. And then we are using these magnetic parts, which you don't see from the outside. They are inside the coil, then here.
Yeah, okay.
And we try to bind the magnetic field in these magnetic parts and make a magnetic circuit.
Ah, right, okay. So this is kind of in there.
Yeah.
Okay. And then there's the plunger, you call it, no? Okay.
Yes, the plunger, yeah.
Okay, yeah, so like that, okay. So this magnet moves this.
Yes, so the stopper is magnetic, this material is magnetic, the plunger is magnetic, and this is the whole circuit.
Yeah.
And in the circuit, you have some gaps here, and this is like a magnetic resistance, and the magnetic force that now builds up wants to reduce this resistance. It wants to reduce this gap, bring everything together that the magnetic circuit is closed.
Ah, right. Yes. Okay. So so it's basically just wanting to have less kind of resistance in itself. Okay.
Yeah.
And that's what we see here.
And this is what we see here. Yeah. These are the force lines, and then you have this resistance here, and now the plunger goes up, and then it's like this perfect circuit.
Ah, right. Okay, so this is before, and this is like, so when the, okay, we see here this is when the plunger is connected. This is the plunger.
This is the plunger, yeah.
Yeah.
Oh,
sorry. I gotta go the other way. Yeah.
It moves from here to here up.
All right, and then now, so do you actually see less resistance in the current when it's closed then?
Yeah. Yes.
Okay.
So optionally, what we also can do is, this is just a nut to screw on the coil, but you could also screw on a Hall sensor that measures the magnetic field.
On top of this.
On top of this,
yeah.
And then it can acknowledge the difference if the plunge is down or up. Okay. So you have an electronic feedback.
All right, but you would already know at least a little bit by seeing that the resistance, the current is less when it's closed.
You are talking about the ohmic resistance of the coil? No, you don't see.
You don't see any difference.
No.
You don't.
No.
So you couldn't see it from the electrical side if it's like this or like this. You could not see a difference. Okay. All right. So now we've understood how the plunger is moved.
Yeah.
So we're actually talking about stopping and starting a gas.
Yes.
So can you show us how that one works?
I mean, It's the gas is in here.
Yes.
And then you just put on the current. It opens the plunger and the gas flows through.
Yeah, but is it a metal sealing, or what kind of, you know, like how does the end of the plunger look?
Oh, okay.
Yeah.
So at first with low pressure, we are using elastomer sealings.
Yes.
Up to 50 bar. It's depending on how you build it in the plunger.
Yeah.
And this is a very soft sealing.
Yeah.
So very good for tightness.
Okay. So
and it gives in a little.
Okay. All right.
But as you can imagine, if you go higher with the pressure, the dynamic stress becomes with every switching cycle harder, and then you need a harder sealing before this gets destroyed.
Okay.
And then you switch to PTFE sealing. This is what's in here.
It's what's in there. Okay. All right.
And this goes maybe up to 100, 160 bar. And after that, you need even harder sealing material.
So tell us a little bit about that, because I know that's interesting. So harder. What sealing do you have here in this one?
Here we are using PCTFE. In some other versions, PEEK, or even metal to metal.
Metal
sealing.
to metal.
Yes.
So you're basically doing railway style, just pressing metal on metal.
Yes.
Okay. So then let's look at this one here. This is basically, at least from what I see, a metal sitting on a metal here. Yeah. So there is no polymer, no nothing. And I mean, like, does that work? I mean, you know, we're talking about hydrogen here, which is an extremely small molecule.
Yes.
And I mean, it's one thing when that's at normal temperature pressure, but when it's coming at 1,000 bar, I would assume that hydrogen would be even more willing to make its way, you know? So, and now you're talking metal on metal. I mean, how much force do you have to apply there? And how does that metal have to be?
The good thing is the higher the pressure, the more force is on the plunger and supports the tightening of the valve. But basically the secret is a very high quality surface finish. So you need a very high quality surface with not any dirt on it, no riffles or anything.
Okay, so you want you want the perfect match, basically. Okay, all right, and you are able to make it that. You know, let me say, what do you even call that? You know, what's the? I think it's 10 minus 3 or what?
It's 10 up to the power of minus 4 millibar liter per second.
Okay.
This is mostly requested with hydrogen.
Okay. For the smoothness of that.
This is like the pressure drop. This is allowed out of the valve when it's closed.
Okay,
you know?
I understood. Okay.
This is a leakage rate.
That's the leakage rate. Okay.
Yeah.
I think I was also trying to. I'm just trying to recall what they're called. You know, these how smooth the surface is. That surface must be super smooth. So you have.
There are like these R max values on the drawings with 0.3, 0.2.
So that is almost going into astronomical. So I know the telescopes and so on. They also have that. You know, when they're making the mirrors, that they have to be very, very smooth. So that means you are essentially making these little surfaces here super, super duper duper smooth.
Yes.
So that you don't need any other form of sealing. You can just press on the metal. Okay. And again, on this side, the high pressure gas is helping to push this down.
Yeah.
And then the solenoid has to pull it up also against that pressure. So you have to have pretty strong.
Yeah.
Cool. So now this one. You said it's an assisted.
It's a servo-assisted.
Servo-assisted. Okay. How does this one work? This is this one, right?
Yeah. So as you already realized, the higher the pressure, the inlet pressure is, the stronger the coil needs to be to lift the plunger up.
Yes.
So now we only have 0.7 millimeter diameter.
Okay.
But of course you want to have bigger valves.
Yes.
Go up to 50 millimeter. And then you would need like a very big coil with a lot of power.
Up. Yes.
But that's not feasible.
Yes.
So you have to change then to a servo-assisted valve.
Okay.
And this is just a picture to show you how it works.
Okay.
So here it's
so this is the cross section of the valve again.
Cross section.
And where's the gas coming in?
So here the gas is coming in.
This way.
The red color is the gas.
Yes.
So now it's here the piston, or in this picture the diaphragm.
Bring that over here. Okay, so this will be
So the gas comes in, and then the pressure is under the piston.
All right. Okay.
So it would lift the piston up.
Yes.
Right?
Yeah,
against the spring.
Okay.
So, but we have a hole right here that the gas can go through the hole above the piston.
So
the pressure builds up above the piston, and there's more surface above the piston than below, because this area is still closed.
Yes.
So the pressure presses the piston down, the inlet pressure.
Okay.
And now if you open this valve through this channel, then here, this goes to the outlet of the valve and releases the pressure above the piston. So then again the force from down under is stronger, and it lifts the piston up. And this is what we call then a servo-assisted valve.
Okay. So which part is, this is the only part that is, let's say, mechanically moving? This?
Yeah, this is moving.
Yeah.
And then, if it opens, the pressure above the piston releases, and then also the piston goes up.
So I didn't say that correctly, but this is the part you're electronically controlling.
Yes.
And basically by controlling this
part
then induces the other motion, basically.
So this part is just like the normal direct acting valve we were looking at before.
Okay. So just looking at the picture again. So the upper part we had here was, this is the solenoid part which you control and which you move. Yeah. And then this. So this opens up, and then takes out the
It releases the pressure.
Exactly, releases the pressure on the back side.
On the back side.
Okay. So basically it opens here. Right. And then this has a chance to escape.
Yeah, so this seat here, this pilot seat, needs to be bigger than the hole in the diaphragm or the piston, that more pressure can be released and built up again.
Okay,
that's very important.
Right, so but the hole is there between.
So here the hole must be around here or here.
Okay.
You know. So this area is filled with pressure, and then through
the hole allows
it's also filled
the gas to go from here to here.
Yes.
All right, because I see here it's closed. And then there must be that little hole somewhere.
This is closed, and this is all closed for the outlet.
Yeah, exactly.
But
so
here it fills
comes
it up.
and then fills up, and then this one lets the air out here, or the gas out here, and then there's lower pressure here, and then this goes boom. Oops.
Yes.
Yeah.
That's right. Yeah.
That's it. Okay. Goes up there. How does it open? Like pluck, at once, or does it open slowly?
And you can regulate that. We have some valves where you can change the diameters of the pilot, or here via screws here of these channels.
Okay.
And then you can regulate how fast it opens. It's really depending on on how big is the pilot seat to the borehole in the piston.
Okay. And this is another valve that would do 1,000 bar type thing, 700, 800 bar.
So this one here, not of this picture, this is just to show you the servo systems, because you see this is like some kind of warm pressed or casting housing. For 1,000 bar, you really need the full bar material.
Okay.
But that would be that.
This one here. All right. Okay, cool. So 1,000 bar, and I can see these things are incredibly heavy. I probably don't know if anyone's seeing this on the video, but this makes me think you're probably using some like good material here and other things to make it safe. Tell us a little bit, how do you make them safe? Because safety is always a topic.
Safety is the biggest topic, especially when it comes to high pressure with hydrogen.
Yeah.
So the first thing, of course, is the design of the design pressure.
Yeah.
So usually we design our valves 5 times the working pressure in the low pressure field.
Yeah.
But because you never know where it's installed, what happens in the system, and if there's a failure, then high pressure might be there. Yeah. But with these high pressure valves, they are working already at the limit of the system,
Okay.
So there we will try to design around 2 times the working pressure before anything is allowed to be damaged.
So you're designing this one at 2,000 bar, more or less?
For example,
Okay, all right, okay.
Yeah. And then what's very important is then the testing. So every valve needs to be 100% tested up to 1.5 of the working pressure.
Okay, so you have a testing facility where everyone that comes up the line gets tested by that
yes,
again?
100%.
Okay.
Yeah.
All right. Okay.
Yeah.
So that means
this is also a part of the pressure equipment directive of the European Union. So they really want to see these 1.5 nominal pressure testings for every valve.
Okay.
To be sure.
Does temperature affect these things a lot? I mean, if I'm operating this at the North Pole or whether I'm at somewhere at the equator, can I use the same valve?
You can, yeah. So we can go down, for example, with these ones to minus 40 degrees. So, and this is what is requested if you want to install a refueling station in Scandinavia or on the North Pole. And this is a good question because when you go down with the temperature, all the materials are getting stiffer, also the sealing materials. And then again, the tightness becomes more difficult,
Okay.
And we have next to the testing bench, we have a climate chamber where we can go down to minus 40 degrees and then test this also. If the customer wants to be sure.
Okay, so and just to understand, we're talking ultra high pressure valves here. Does it make a difference, let's say from the norms and so on that you have to adhere to when you come to these kinds of valves? Do you have an ultra high pressure norm?
Yes, kind of, yeah.
Oh, yeah?
So the I was talking about it. The pressure equipment directive from the EU, I think, is the biggest one.
Okay.
Because they are categorizing. So on the left side you see hazardous gases like hydrogen. On the right side it's a little more easier. And then when you see here, it's depending on the pressure range and the volume of the vessel. So these valves are just dedicated to the vessels. And when you go above the 1000 bar, you are at category 4. And this is the hardest category. And this means an external institute, in our case TÜV Süd, is coming once a year, auditing us. And they are not only checking, are we using the right materials, are we testing right, they're also checking, is the calculation tool or the design tool the one that brings us to these valves and to a safe space here.
So they actually check also your design process in that sense, and they check if your calculator is working correctly.
Really. It's the hardest category. And we are also sending every year the valves outside to an external test to have an individual testing to be sure.
Do you see failures with these kinds of valves at all? I mean, what could be? What could even happen?
Well, we assume that you are choosing the right materials, of course. I think one of the first failures is leakage. So in a fueling station, they usually, in every compartment, they have a sensor, a hydrogen sniffer, monitors the interior. And then when it goes up, then there's... Then the system needs to shut down. Somebody comes in, sniffs everything, And then, for example, here we have, what is this?
This one?
Oh, I'm scanning it. Here, for example, For example, at this valve.
This one, this is quite an impressive one. Maybe you must say this. This is also a assisted one. No.
This is a direct acting one.
Direct acting, okay.
But this is not a solenoid valve. It's a pneumatic actuated process valve.
Aha, okay. So that's true. We only talked about the solenoid valve. This is a good point that you're making. So this is actually, so it's not solenoid, so not electric.
No, it's controlled by compressed air, 6 to 10 bar going in here. So you see, this is a plunger, a cylinder. The spring holds it down. This is directly connected with a spindle to this part here, where also the sealing is. And if you bring compressed air inside, then it lifts up. I think I'm not strong enough.
It's a bit of a strong.
It's very strong.
One. Okay. Well, that's actually good that we picked this one up now because, like this, we see that ultra high pressure valves can be done with the solenoid and also with a gas, with pneumatic. Okay. So
with these pneumatic actuated valves, sometimes with bigger sizes, you can reach a little more pressure range with a reasonable.
Where would one use these? Where would I go to find this?
So it's really mostly depending on the customer, what he is used to, if he has in his facility pressure, or he doesn't want to use any pressure on only electrical power.
So like at a refueling station for vehicles, for example, are these used, or that would be rather more the magnetic ones?
Yeah, we see, at refueling stations we see a little more of the process valves because they have compressed air.
They already.
And then, for example, with an electrolyzer in the field, there's only electrical power, and then it's more like the solenoid valves.
Okay. What about in a truck? Is this a kind of valve that also sit in a vehicle actually, or it's more for stationary applications?
So our valves are more for stationary applications.
Right, understood.
For mobile applications, you need a lot of more standards to fulfill. And they are on trucks for the stationary fueling.
Yeah. Okay.
So if they are standing down, then our valves also are doing the fueling. Yeah.
Okay. Cool. And
in general, you are starting from an electrolyzer with the hydrogen production, and by the end you need to compress it to high pressure and store it. There our valves are in there, or the ultra high pressure valves, and then through the complete transport right until the end where maybe a stationary fuel cell is headed before the fuel cell, then also these valves.
Markus, I have two more questions. One is, I wanted to know, because I know you've been designing these, what does it take to keep your valves happy? You know, so you're designing a system and you've got 10 of these. And what do I need to think about that they were working, and can I use those valves forever then?
So how to keep them happy? Happy valve, happy life. Yeah. First thing, I think most important thing is that everything is clean in the system.
Yes.
Yeah, you don't need any dirty media, and of course not any equipment. This is also because of the very hard ceilings.
So you don't want dirt.
Because if there's any dirt in there, then the hard ceilings, if it touches one thing, it can immediately have leakage.
All right,
a small leakage maybe, but for hydrogen, of course it's enough.
Okay.
So a lot of filters I would recommend to keep them happy.
All right. Okay. Good.
And they are IP65 protected, and mostly they are indoors, but of course unnecessary heating and water splashing you don't really need. And the most important thing I would recommend, especially for very high pressure valves, is that you have regular maintenance. Maybe once a year or every 80,000, 100,000 cycles.
And what do? You clean them in the maintenance, or what do you do?
You clean them so they come back to us.
Okay, you have to take them out and then bring them back to you, and then you screw them to the whole thing.
Out,
okay. So I can't be running my system, or I need to switch with another one.
If you want to the system continuously operating, then you should switch it.
Tell us a bit of an outlook. So I mean, we've looked at safety, we've looked at how they're made, and I know you've been designing and doing these things, and so I know you're somebody who probably also sees what's changing, what's coming. So Markus, can you give us some insights there?
So based on ultra high pressure valves?
Yes.
Well,
where are we going? Are we coming to even higher pressures?
I think so.
Yeah?
I think so, These 350 bar for commercial vehicles and 700 bar for private cars. I think we're not satisfied in the long term with that. We want even higher valves. So the main knowledge here on these valves, I think, is the material selection, the surface treatment. You can do special coating. And I think we did not reach the limit yet there. So maybe we can still improve that and get a higher service life, that you don't have to maintenance. Or if they are deciding to go up with the pressure, then we need to do this to keep up with the higher pressure ranges. Maybe in the future it will be 500 and 1,000 bar. Then for filling you need even higher pressure range.
Wow. Well, okay. So that means more pressure coming up. That is good. Markus, thank you. This has been an extreme pleasure having you and your valves here. Thank you very much, and thank you for watching. I hope you've enjoyed this, and we now know a lot about ultra high pressure valves. If you like this, then please give us a like or subscribe. Also, you need to know that on Hyfindr.com you can get in contact with people like Markus and many other components that you need for the hydrogen economy. All these components are great and available, so no excuses that the hydrogen economy is not working. It's all there. Thank you very much for watching, and have a wonderful day.